Hello everyone, I am Dr. Satyanarayan Rao, and today actually we will look at something that's interesting about the deep learning models, specifically how they see the images. And it's very interesting that these models can be tricked into classifying. It's very easy to fool them. For example, what we think is that once we train a model with hundreds or thousands of images, it works well, like it can classify dogs, cats, or peoples, or type of vehicles. We have seen these image classification models based on neural networks, but by changing few important pixels, which is actually almost invisible to us when I display these modified images to the human eye, we can actually make these models to completely misclassify into wrong predictions. So this tiny or carefully designed pixel manipulation is called as adversarial attacks. So they can actually make these deep learning models misclassify a dog as a cat, or even a pedestrian as an empty road, or it can misclassify a healthy lung as a cancerous one. So this actually is really important to understand adversarial attacks, because imagine that in a world where there is self-driving cars, if someone injects this kind of virus where your image classification identifies a stop sign as a green signal or a pedestrian as an empty road, then you would be in trouble. So we can make people get into trouble by this kind of attacks. What we will do is actually we will recreate the whole process ourselves using a well-known image classification model, and we will slightly modify the pixels in the image that we cannot identify, but you can see that how the accuracy of classification drops when it is subjected to adversarial attacks. And we will also apply some small defensive mechanism to make the model little bit more robust. First, what we will do is that we will talk about all the libraries that we are using and the data set, so that we have the idea that what we are going to do, and then we will explore basic ideas behind the adversarial attacks, so that everything makes sense when we finally look at the code. And so let's begin by looking at the libraries that we will be using. So first we are going to use PyTorch in our analysis or the pipeline. So we know that PyTorch is a deep learning framework. It can handle tensors, and it also handles GPU operations. So we know that Kaggle also has GPU compute for free. So we will use it to define our model, run our training, make predictions. So the next software that we will use is the Torch Vision. It's actually an extension of PyTorch that actually gives us some ready-made image data sets and some pre-trained models. For us, it's actually what we will do is we will load one of the image data set that is known as CFAR10. The main toolbox here we will use is the ART. It's the Adversarial Robustness Toolbox. So instead of writing our own attack code from the scratch, like how we manipulate the pixels to fool our image classification models, we will use the ready-made implementations. And what we will do is that we will also use a pre-trained model known as ResNet 18. It's a very popular neural network. 18 here says that it has 18 layers, and it's actually pre-trained on ImageNet, a dataset. So it knows some good visual features. So having covered all the libraries that we will be using, now let's look at some of the theories that are behind the adversarial attacks, and some simple defense mechanism that we can use. So let's get started from the image classification basics. So we know that how the image classification works through the use of neural networks. So these neural networks actually learns patterns from thousands of similar images, and it learns some patterns. And so now if we put a new image, it gets processed through these layers, and it produces a prediction, which is it classifies the image based on some known classes. For example, if we train the neural network from thousands of dogs and cats images, and when I give a new image, so this network with its learned pattern can predict if it is a dog or a cat with some confidence. So the score tells us how confident it can predict if it's a cat. And now what is this adversarial attack is that when I take an image and if the model is correctly identifying it as cat, and I can add some tiny pixels or change some color of the pixels at its mouth or eyes, do some tiny changes on the cat image that will look cat when I see that, but this tiny image are not visible to the human eye. It will fool the trained neural network into misclassifying it as dog. So the model is convinced that it is dog even though the changes that I did is invisible. There are two types of attacks actually. One is the FGSM attack, which is known as the fast gradient sign method. The other method is the PGD, projected gradient descent method. So this first one, the FGSM, stands for fast gradient sign method. This is actually, we can think of it as taking one big jump. The attack looks at the model's gradient, how the pixel changes, which direction if we manipulate the model, it will confuse the model most. Basically, it looks at the gradients and see where we should manipulate so that it confuses the model most, and then takes a single step in that direction. So it's based on the gradient. So it's very simple, like so it's like if you want to spoil a painting, you're just throwing something on that, like a water or something to spoil entire image. PGD, projected gradient descent, it's somewhat more sophisticated. So instead of one big jump, this method actually takes many small and careful calculated steps. It may take 10 or 20 iterations, each time moving slightly in the direction that fools the model, so that after each step it actually checks if it is within the allowed noise limit, and then takes another step in the image manipulation, so that finally the manipulation is in such a way that it's a multi-step one, unlike the previous one, and then finally, like, it's carefully changing the painting with a brush. Previous one, we just throw a bucket of water on the water paint. Here we also know the painting, and we manipulate pixel by pixel at different location to actually change the painting. And so we will use these two kinds of methods that are already implemented in our library, and so we will use that. And we will also see how we can defend against these adversarial attacks. So here is the notebook. So first what we are doing here is that we are installing our Adversarial Robustness Toolbox, or ART here, and this is a library from IBM, as I already said. So I'm going to use Google or Google Colab or Kaggle. It takes, if you see in the Kaggle, it takes around 11 minutes to run using GPU. So make sure that in settings you enable the GPU. And once we install that, what we will do is we will import several libraries, PyTorch for deep learning framework, and NumPy and other things. So if you can see, we are importing several libraries here. We are also from ART, we are importing fast gradient methods, that is the FGSM, that's a type of adversarial attack, and even PGD, projected gradient descent. These are our attack classes. We also import PyTorch classifier, which is also a wrapper that lets our ART model to talk to our PyTorch model. And also we need a few random seeds here. So this ensures that every time we run this notebook, we get the same random samples. This is actually important for reproducibility in research. We also check, like in Kaggle it's available, but if I use Colab, if the GPU is available and what type of device it is. So when I execute this, I get CUDA. So CUDA and GPU is available in the Kaggle, and if you see only CPU, it means that GPU is not available. And now actually we will load our CFAR dataset here. So CFAR dataset is a very famous benchmark in computer vision. It has 60,000 tiny images of 32 cross 32 pixels, and it is divided into 10 classes: aeroplanes, cars, birds, trucks, frogs, horses, ships. Like that, there are 10 classes of different objects. And we use a pre-trained model, RES 18 model, that actually uses 224 cross 224 images. So we have to resize this. So here we are actually just loading our CFAR data model. And here if you come, we are actually normalizing the images, because we are going to use ResNet 18 model that uses only 224 cross 224. So we are resizing the image from the CFAR dataset to this 224 pixels, and then we are also converting it into tensor here, and it also actually we are normalizing it all the pixels from 0 to 1, because now we have 225. 0 to 225 is the pixel ranges, and that we convert it into 0 to 1. It's a standard pre-processing. And then here if you see, we are actually the data set. So we are downloading all the data set. It has like 10,000 images. This is where we download all the data set from the CFAR data set. And then we have the known class names here, and then we have some print statement to see if our data has been loaded. And more importantly, here we actually load the data with a batch size of 64. We don't load everything at once. We use like a batch processing because the Kaggle has limited GPU, and so it's efficient for GPU processing that we do any task in batches. And then you can see that it took some time, and then it printed all the class names. You can see here aeroplane, automobile, bird, all these are the CFAR dataset, and it loaded all the 10,000 images. And here I am actually visualizing the actual images, like to know what we are working with. I'm just denormalizing it and using some matplotlib functions to actually plot some of the pictures here. You can see a bird, automobile, dog, cat. So I'm just plotting some 6 images here. And why we want to see here is that this is the clean image that we have, and soon we will see the adversarial versions after it has been manipulated or corrupted, and see what exact images that can be used to fool our model, RES 118 model. And in the next step, what we are going to do is that this is the step 2. What we will do is we are using ResNet 18. It's a popular convolutional neural network, and this is a very lightweight model, and we will adapt it for our CFAR 10 dataset by replacing the final layer and then fine tune it for few iterations or epochs. Let's see what we are doing in this cell. So first here we are actually defining the model as ResNet 18, and these models come from our if you see here where was the models, it comes from our Torch Vision library. So there are many models, and ResNet 18 is one of the neural networks that can be used for our image classification studies. Here it's the usual pipeline that what we are doing here is that we are defining the layers, and for every features we are defining we are defining that there are 10 classes here. And so we are here telling that train equal to true. So we are training the model with all these variables we are using Adam optimizer with some learning rate, and it also uses the smart gradient descent algorithms. And now we print what happens during each epochs, if it is training, and how accurately it can actually predict or classify different images. And you see that it starts with 76.24 accuracy and slowly jumps as the iteration goes on. The progress is being printed here, and the model is learning. And even after 3 epochs, we have a model that is over 94% accurate. So 94% of the time, it can clearly classify the images with different classes. And this training actually takes a few minutes, and it's perfectly doable on the Kaggle free account or Google Colab. And so once the training is complete, we can use the model for evaluation. And so we have a function that is defined to evaluate the model. What it does is that it loops through all the test data, get the model prediction, and compares it to the true labels or the true classification. And it calculates the percentage of correctness, like how accurate it predicted the correct class here. So dog for dog, not dog for cat. So when I run this function, what we get is that the model is actually 90% accurate. So yet we have not actually corrupted the model. So this is like a baseline. So every adversarial attack that we do will be compared against this number. So how the accuracy drops. This is the best accuracy that we can achieve with this model. And now we will use the same model but with corrupted images. So in the step 3, what we are going to do is that we are going to corrupt the images. We will put small invisible perturbations to our images with an intent to fool the machine learning model. As a human, I will see no difference, but the models can completely misclassify because of these attacks. So we are going to do 2 steps. One is the FGSM, as I already said. It has a formula here. This is the way we are actually adding the perturbation. And there is another way, projected gradient descent. Here it's much more complex, but you can see the mathematics of these 2 techniques in any online resource. But basically, as I said, one is a single step attack, one is more of a iterative kind of attack. And so we will implement these two. These are actually already within the ART library that we used. We have imported already. So what we are doing here is that we are actually defining our ART classifier. So it gives actually the ART the access to the PyTorch models, the ResNet model that we are having. So these are required by, it's like an interface between PyTorch and the ART. That's what we are doing here. We are wrapping our model for the ART here, right? Here what we will do is that here first we are going to implement the FGSM, the fast gradient sign method. So we are not going to use all 10,000 images because it's not doable in the Kaggle. So we will choose only 1000 out of 10,000 test images because of memory issues. And we will see how the accuracy drops after implementing this attack. So this is the part that we are doing it. So we have a ready-made function, FGSM attack, from our ART library. And so we have generated the examples here for our 1000 images. So what it does is that For every images, we perturbate by a small value that's defined by this epsilon. So this is the epsilon that we have defined it. It's a small number which we have taken it as 0.03 here. So with this small number we will add the perturbation. So it's just 3% perturbation. And it takes 2 to 3 minutes for this 1000 images. And now we have 1000 image that will look identical, but it has been attacked by this FGSM adversarial technique with the 3% epsilon. Now if we use this images, the same model to classify, the accuracy should be very low as compared to what we had for the baseline here, right? The baseline model we had around 90% accuracy. This is the clean accuracy. Now we have a corrupted image by FGSM method, and we will also implement the PGD method. So it's more of iterative. We will use the same epsilon here, right? But it also has a new function, a new variable here as epsilon step. It's the step size for each iteration. So instead of jumping 0.03 all at once, it will, for each iteration, it will corrupt by this 0.01 epsilon, right? And it will, since it's iterative, we have to define what is the maximum iteration. So here the PGD algorithm runs for 10 iterations. So each iteration moves in a gradient direction by 0.01 and checks if did it exceed the epsilon budget of 0.03. It will come back to the boundary and repeat it. It's like the previous one, FGSM, but instead of doing it all at once, it's doing iteratively. And it's also within the art library. So we are not going to implement it with Scratch. So we are just going to use it. And similarly, we have now 1000 images corrupted by PGD technique. It has been attacked, corrupted, and we will see how these two techniques evaluates against our, like we will evaluate the adversarial examples with the clean one, right? So we have a function written for it, evaluate adversarial, and this function is actually similar to our clean evaluation, but this actually handles numpy arrays and processes in batches. So you just run it and you will see that the evaluation runs and prints the accuracies. So what we get is here the clean accuracy was 90% as we saw earlier. When we attack it with FGSM all at once, it's 60%. It drops by 30%. The model went from getting 9 out of 10 right to barely 6 out of 10. And when we do PGD, as I said, it's iterative, so it's more harmful and more damaging. You see, the model is only getting 3 out of 10 accurate. So it's even worse than a random guessing. Like if there is 10 classes, the random guessing should give at least 50%, right? It's worse than random. So if I emphasize this, think of a moment. We changed the pixels by 3% in the normalized space. So from 0 to 1, if it was 0.4, I just made it 0.43 with these two techniques, and you see how it's destroying the accuracy. And let's see some visualization of these images. So we will compare clean image with the two techniques that we used, and see here is the accuracy plot when it's a clean image, the clean model. So imagine this is our deep learning model, and if it is attacked by FGSM method or PGD method, these are some simple techniques where we can corrupt the images to fool the model, confuse the deep learning model here. By the way, I will share this notebook on the GitHub. Leave all the source code in the description below. So here I'm just comparing the images, original versus FGSM and PGD. So they all look the same to my eyes. So this part I'm just plotting it just to see if there is really, you see these planes look almost identical, but it was predicted wrongly. Here, this plane here was predicted as truck. They all look the same because we have manipulated only 3% of the pixels here. But still, you see, this is what adversarial attack look like? These attacks know exactly how to fool the model to get your switches in the neural network, the sigmoid function or other things to actually go in the wrong direction. These are our summary here I have printed. And as a small mitigation technique, what I have done is that we will use some simple JPEG compression to actually see if it helps. Because what happens is that the adversarial noise actually affects it, the perturbation mostly affects the high frequency pixels. So when the pixel values are changing rapidly. So when we compress the image and then decompress it, it's like a smoothing out, and this adversarial noise smooths out while keeping the main features intact. That's the idea. So what we will do is that for each image we will denormalize it back to 0 to 255 pixel, then convert it into a image object, and then we will compress it. What we will do is compress it with a quality of 75. The quality ranges from 1 heavy compression to 100 with minimal compression. So we will put something like 75 somewhere. Let me see where. So here we have defined it as 75, and so when we compress it and apply the same adversarial things to the compress and decompress it, what happens is that to the attacked images, the perturbation gets smoothed out and we should see an improvement. So here, so this compression is, we call it as defense. So with no defense, it's 60% accurate, the FGSM. With a compression, we get 74%. So 14% has been improved. Similarly, for PGD attack, it was 36%. So, but when we use compress and decompress it and then use it for classification, we get 66% accurate. So it's 30% higher accurate. So this is exactly the thing, like say simple JPEG compression actually can work sometimes, and that's what we need to do. Like it was like a pre-processing step. It's not exactly a defense, but what we did, it was a simple pre-processing. And if you see, it actually works best with the PGD attack. If you see, like PGD was a iterative process. So it creates a structured high frequency disturbances. So when you compress it, it removes, compress and decompress, it smoothens out. And so that's why we see a drastic 50% improvement here. And so this is all about the adversarial thing. And I hope you learned something watching this video. Remember to stay learning and enjoy life. See you with another video.